So, good morning to everyone, and the topic for today is given to be arrangements, right. So, for those of you who are not familiar with this term, and I will certainly define these. The plan for today's lecture, I have 2 lectures of 1 hour slots. So, I plan to cover essentially notions like duality, okay. Then I will introduce what is called lifting transforms. So, I believe we have gone through already some lectures on Voronoi diagram. So, this may be a familiar term to you, right. Yeah, fine. So, lifting transforms and what I call minimization diagrams. So, all these terms I will explain, and then levels of arrangements. Then I will show a connection between something which could seem a little surprising, but it will fall out of all these techniques that we are developing. So, the inside outside circle queries. Oh, I see. Okay. I will make it bigger. So, somehow here it looks much bigger. Okay. And then, and is that fine? How does that look? Readable? No? It will be hard for me to write anything bigger than the last line, but because otherwise I will just fill up everything within like 2 or 3 lines. So, what is the issue? I will just come behind to check what is coming. It may not be the size, it may be my handwriting actually. Okay, I'll do the last font. The last font I will. Okay. Zone theorem. And then I have some tutorials in the afternoon. So, for tutorials I want to do some applications of some of these techniques and something about sum of squares, of faces, largest, smallest triangles, and so these are applications of the techniques that we develop. Okay. So, the first topic is the dual transform. So, has dual transform been introduced formally? Only for that lifting transform. Okay. So, good. So, in fact, it is a step back. Actually, the lifting transform follows from the dual transform. But before that, let me give you some idea of what I mean by arrangements, etc. Okay. So, suppose I am given lines . These are infinite objects, right. So, I am given a set of lines, and I want to do some kind of processing, pre-processing. So, build a data structure to do point location. So, by which what I mean, so I am given this set of n lines. Okay. So, let us say this L is set of n lines, L1, L2 up to Ln, okay. And I want to build the data structures on L such that given any query point like this, let us say here, I want to actually report which line lies directly above this. Okay, it's like I shoot a ray, a vertical ray, and whichever line it hits, that is the answer to this query. Okay. So, if this happens to be, let us say, I have L1, L2, L3, L4, L5. So, I think I covered everything, L6, etc. So, if this is the query point Q, then the answer to this is L1, right. So, this is L1. So, this is quite a standard problem in geometry. Now, how do you go about solving this? Well, one possible technique, very simple technique actually, is it's like a generalization of the binary search that you do. So, if I had one dimensional objects like points on a line, if I had a situation like this where I was given these points instead of the lines, and then I wanted to do some kind of a binary search, query. Suppose my query point is here and these are my points P1, P2, P3, P4, P5, P6 and so on and so forth. Suppose I have some n points. Then the simplest thing would be to sort these points, okay, and just report that Q lies between P5 and P6, and this you can do it with a binary search, right. So, binary search tells us that Q is between P5 and P6. Okay. So, for that I have to sort the points and build the data structure, and then I just do the binary search using the x coordinate of Q. Now, here it is a two-dimensional problem. Okay. So, what I can do is, to extend that, I can pass a vertical line through every intersection point. Okay. So, these n lines, so first observation is that n lines intersect in n choose 2 distinct points. Now, you may question this, that what if I have a situation like three lines passing through the same point, then this n choose 2 will not hold, right, it will be less than n choose 2. But I am assuming, again, this is for the sake of making some of my arguments simpler, not that it will not hold otherwise, is that it is called a simple arrangement. So, simple arrangement means basically no three lines are concurrent. So, this kind of situation won't occur. So, I am guaranteed by whatever means that it won't occur. So, just to keep my argument simpler. So, they are n choose 2 distinct points, and I am going to draw vertical lines through each of these points, each of the intersection points. So, let me not draw all of them because it will just clutter up. Now, if you see the vertical lines, okay, the vertical lines are, again, they intersect the x axis in some points, okay, and this is, we can capture that using, let us say, some x1, x2, x3 and so on and so forth, right. Since there are n choose 2 distinct points, there will be about n choose 2 such x coordinates. Right. Now, if you look at two consecutive coordinates, okay, there cannot be any intersection points in between, right, because by definition I have drawn a vertical line through every intersection point. Right. So, if I blow up this picture within a so let us call them vertical slabs. So, within a vertical slab, okay, if I expand this, so now I am just going to blow up this vertical slab. Okay. So, the situation looks like something like this, and there are lines crisscrossing. And there cannot be any intersection points here, right? No line can intersect, because if there was a line intersecting, I would have drawn a vertical line. Right? So, they do not intersect. Right? Now, this structure has a very nice property. This is a vertical slab. Observation, no intersections. Since there are no intersections, okay, we can therefore we can order the lines within the slab. So, how do we order them? What do I mean by ordering them? So, yeah, it is like a above below ordering, right. So, it is a above below ordering. So, if I just give it some names, let us say L prime 1, L prime 2, L prime 3, L prime 4, and all the n lines will cross, because there are n of them, right. So, I have L prime n such vertical lines, such lines, and I can say that within the slab L prime 4 is above L prime 3, L prime 3 is above L prime 2, and so on and so forth, right. The ordering is not going to change within the slab. Now, in another slab they may intersect and change the ordering, but within a particular slab the ordering is fixed. Now, once you have an ordering, you can do binary search. Okay. So, let us go back. The problem that we started with was given a query point Q, which line lies directly above Q. So, the first thing I am going to do is do a binary search along x1, x2, x3. So, one binary search will tell me which vertical slab contains this point, right. And the next binary search, okay, now suppose Q was here, sorry, suppose Q was here. Now, I basically I will take these lines, okay, put them in a different data structure, okay, and I will do a binary search using the following thing. We will look at the middle line, is Q below this? Yes, then Q must be occurring here, and so again I do a above below test. Okay. So, the above below test is point above, so point above below a line, and I am sure you know using your coordinate geometry how to do that, whether the point is above the line or below the line, and therefore, I can easily find out again that within the slab the Q lies between L prime 3 and L prime 4. Okay. So, I can answer the query that we started with using two binary searches, right. So, two binary searches yields the required result. So, that is 2 log n. So, query time is, or which is basically order log n, right. So, we are basically back to the situation of one dimension, where there you took one binary search, this takes two binary searches, okay. And this idea actually extends to higher dimension also. Now, I can't draw those diagrams here. Suppose instead of lines we had planes in 3 dimensions, okay. So, this idea actually can be extended to the planes and even in d dimensions, okay. But then if you go to higher dimensions, you will require more and more binary searches, okay. So, let me not go through this, maybe if time permits, in the afternoon tutorial we can look at that, okay. But right now let us move on. So, this is basically one of the most fundamental problems for arrangements. So, this is arrangements of lines, okay. Now, this word arrangement actually applies to any kind of linear varieties in higher dimensions. So, this is lines in 2 dimensions. So, in 3 dimensions, normally by arrangements we will look at again hyperplanes or planes in a certain dimension. Now, the more general notion of arrangements extends to other kinds of curves. Okay. So, that is somewhat beyond the scope of this lecture. So, we will not do that, we will stick to the linear ones only. Okay. Now, let us look at another problem which may not look very related, but then I will establish a certain relation. Okay. So, now we are instead of points we are given, so instead of lines we are given points. These are points in 2 dimensions. So, suppose again this is a set of n points, and now I want to build a data structure that supports half-plane queries. Okay, what do we mean by half-plane query? Well, it is like this. So, if I am given a line, so now my input is a set of points and my query is a line. And I want to know, let us say, on how many points occur below this line. So, it could be a counting query like how many points, or it could be which points occur below this line. Okay. Below means the one that contains the y equal to minus infinity, above is the plus infinity. Okay. So, it could be either how many or which points, which ones lie below a query line. Yeah. Okay. And it not be this query, it can be any query, right. So, this is just one of the possible queries. How about we could have like this L prime, clearly L prime and L will have different answers. Okay. But on the other hand, let me also point out that if this L, okay, is just perturbed a little bit, the answer will still remain the same, right. So, although there are infinite possible lines, okay, the answer to the query is not all infinite possibilities. Okay. In fact, it will be very, very limited. Okay. So, the something to ponder about is that how many distinct answers are possible. Distinct answers are possible. So, what I mean is that this L, and let us say I take another L, very close but not quite L. So, this red line and the purple line, they will yield the same answer. Right. So, the question is how many distinct answers are possible. Now, if you do just a very naive kind of an argument, there are n points. Okay. After all, what is happening? The set of points is being partitioned into 2 parts, right. So, how many partitions are possible essentially, that is what it comes down to. How many so this depends on how many partitions can be induced by lines. And the naive answer would be that there are n points, how many possible subsets are there? 2 to the power n, right. So, either the point is in the subset or not in the subset. So, that is a large number, huge number, exponential, right, 2 to the power n. But again, without going into the details of the argument, I will actually establish this, that only about order n square partitions are possible and not 2 to the power n. Okay. I will establish that actually. Okay. So, this is a little bit of a surprise, and that comes from geometry. So, if it were just arbitrary points in sets, okay, okay, then I could have partitioned it in any way I wanted. Okay. But here the problem is that if I want to just have these 2 points, these 3 points in one partition, okay, and the rest of the points in another partition, then the line has to bend. So you can't keep it linear and do it. Okay. So that's the constraint because of which all those exponential partitions are not possible. Okay. But there is a, I'll give you a simpler argument. This is just a hand waving intuitive argument. Okay. Now, how do you go about solving this problem? Well, so this is where basically I'll introduce this notion of duality. Okay. So I'll define a transformation. Okay. Duality between. Okay. So if you go back, I started with basically this problem where the input was lines and the query was a point. Okay. Then I showed you an example where the input is points and the query is a line. Right. So it turns out that these are not that different. Okay. The points being input and the lines being input and the query point, they can actually be transformed to each other. Okay. So essentially it's a transformation which will map points to lines and vice versa and maintain certain properties, and that we'll exploit. Okay. So duality between lines and points. So suppose the point, so let me make sure I stick with my notations. So I am given, let us say, a point P with coordinates a b. Okay. And here is a line L, okay, which has the equation okay. So this is your slope intercept equation, and here is a point P. And intuitively what's happening is both are basically defined by 2 parameters, right? A point has 2 parameters and line also has 2 parameters, and therefore we will be able to define this transformation, relatively easily. So I'll define this duality transform d of p as, so this point is mapped to y equal to 2ax minus p. Okay, and this line will be transformed to, so let us say d's of L will be alpha by 2 comma minus beta. Okay. And you can quickly check that d of p is p and d of L is L. So it's self inverse. Okay. Technically, the only problem happens for vertical lines. Okay, then alpha becomes infinity. So I am not defining it for alpha equal to infinity. Instead, I will assume that there are no lines. We will be able to avoid the vertical lines. Now, if it so happens that there are vertical lines, we can do just a minor perturbation of the coordinate system and can make sure that no line is vertical. Okay. You must, yeah. That's the transformation, the dual transform. D is, okay, so strictly speaking, I should actually say that, D maps basically, in this case, points, so it's basically a transformation like this, that's all, by which I am able to basically define both of these, that dual transform of a point is given by a comma b is given by this, and okay, let me use different notations, maybe, okay, I got carried away. Let me use a notation like this, prime instead of this, just to keep it separate. Say it again. Yeah, so then I'll have to apply the, so I have to change this then. I have to say d prime of dp, and you're right. I have to clean up my notation there. This is notational convention. So that's why I didn't want to use two different notations, that's all. So this is the point to line transformation. Now, how did it come from and how can it help us? Okay. So let me give a pictorial this thing, interpretation of this. So this is y equal to x square. This is the unit parabola. Okay. Now, if I take a point P, let's say a comma b, okay, and I vertically project it on the parabola. Okay, so it basically becomes a comma a square. And I draw a tangent through that point. Then this point is actually mapped to a line, okay, which is parallel to this line, okay, and above the parabola. So it has the same slope, okay, and so this will be d of AB. You have a question? You can't read this? Oh, that one is a comma b, d of a comma b. Maybe I could just write it as P. And likewise, if I were to show the interpretation given a line, what is the point? You take that line and move it till it become tangential to the parabola, okay, and the point will be on the other side of the parabola. So it's a kind of reflection on that parabola. And these equations tell you basically what is this distance, okay. So the distance from the point to the parabola, the point to the parabola will be same as the distance from the point to this line. So let me prove it for you. I just write it down for you. Okay. So vertical distance between So let's look at the vertical distance between point P and point L. Sorry, not L, but D of P. So the equation of the tangent is what? It's y equal to 2ax minus a square, right? So the distance from the point to the projection on the parabola, okay. So this distance is a square minus b. and what is this distance? This will turn out to be, let me use a different color, 2a square minus b. You can just solve that because the dual is this line 2ax minus b. So, you can just calculate this distance. I am not doing all the calculations here. So, you can do it, very simple calculation, right. So, I am claiming that, so this point is mapped to this line. I know the equation of this line, okay, and the distance between this projected point and the vertical intercept is 2a square minus b, and then you can show that basically this is the midpoint, right. So, it is reflected around that parabola. So, 2a square minus b and this point. So, this a minus a comma a square will be basically the midpoint between these two. So, you can show that, right. 2a square minus b plus b is 2a square divided by 2 is a square, right. So, basically that line is tangential to the parabola and shifted exactly by the same distance as the point is from the parabola. So, that is the geometric interpretation of this transformation. If you take a different parabola, this property may not hold, but we can take a different parabola also and define the transform in that way. For our purposes, it won't matter, but unit parabola basically becomes easy for us to handle. Any questions? Now, let me show some more properties, and let us look at the vertical. So, P and dP is the same So, let me complete by saying that distance. So, what should I say? Let me call this P prime, okay. It is getting cluttered. So, let me call this P prime and this is called P double prime, okay. So, what I am saying is essentially P prime. So, distance between P prime is the same as the distance between P prime and P double prime. That is what I have proved, right. So, it is a reflection around the parabola. Now, let me establish some other properties, which is properties of dual transform. One, vertical distance between P and L is preserved between d of P and d of L. Okay. So, let me just do the calculation. So, again recall that P is mapped to PAB is mapped to 2AX minus B, and L is mapped to Y equal to y is such that x beta is mapped to alpha by 2 comma minus beta. This is the mapping that we are using for dual transform, right. Now, the vertical distance between P and L is what? We just substitute the coordinates, right. So, vertical distance, let us call it vertical, between P and L is B minus, I will substitute x equal to A. So, alpha A plus beta, right? And vertical distance between d of p. So, I am using d only, like instead of using d prime. Okay, so just being a little sloppy here. Yeah. So, again you substitute what? So, it will be minus beta minus alpha A minus B, that equal to B minus so, it is the same. So, I just substituted, now I am using this point, right. So, this point and this line. The distance between this point and this line, distance between this point and that line is exactly the second expression. So, the vertical distance between the point and the line and the duals remain the same. Okay. And one consequence of that is the incidence property. This implies, so that is basically equal to vertical distance between d of p and d of L. This implies that if p is incident on L, then d of L is incident on p. Oh, sorry, dp. So, the incidence property is maintained because the vertical distance becomes 0, right. That is vertical distance equal to 0. Okay. So, this is one property. The second property, I will leave it up to you to verify, that it is the above below property. If P lies above L, okay, then d of L lies above d's of P. Again, you can just substitute those equations and verify this. Right. So, these are the two very useful properties of dual transform. One is that the incidence property is maintained, including the vertical distance, and the above below. Now, I will exploit, let us go back to the problem of this query given a set of points and a line, which points lie above the line, below the line, right. Now, if I apply a dual transform to this problem, what happens? The line become point and the points become lines, right. So, I am not scaling up in this way, but I am just saying that the points will become lines. Okay, like this, okay, and these lines will become points. So, this line basically, now this is the d of L and this is the d of all these points pi. So, we want to, in the original problem we had to find out which point lies above this line, right. Now, in the transform problem it becomes what? What does it become? So, if this line is above a certain point, then the dual of this point will be above the dual of the line. So, which means that if I, for this point, to answer this query, I just have to shoot a ray and all the lines that it intersects basically is the answer. Because that is exactly the set of points that was above the line. Okay. So, from the problem of finding which points lie above, which points lie above a certain line, we can, using the dual transform, reduce to a problem where which lines lie above a query point. And now you can actually go back to the previous solution. So this not only can answer the visibility query, that which line lies exactly above that, I can actually compute this answer and store it, right, within this vertical slab. Within the vertical slab, okay, all the lines that lie above this is the answer. So we've actually solved the problem. The dual transform basically gives us the ability to do a 2-for-1 deal kind of. By solving this problem, I am able to solve the other kind of problem also. Okay. So let me show you some more connections. I mean, some more applications of the dual transform. So you must have done some lectures already on convex hulls, and okay, how about intersection of half spaces, half planes? Okay. So convex hull problem, basically given a set of points, okay, I want to compute this boundary. This is a convex hull. Now similarly, if I am given a set of half planes, so half planes basically means that this is the half plane I am referring to, this is the half plane I am referring to, right. So this area enclosed by all the half planes, which is basically this shaded portion, that is the intersection of these half planes. Now both structures have some similarity. Can you tell me what? It's a different kind of problem. One involves a set of points, and the other one involves a set of half planes. But there is some similarity about the final structure. What is the similarity? What is the most important property of a convex hull? It's convex. What is the structure that I have got out of the intersection of half planes? It's also convex, because a half plane is convex, intersection of convex sets is convex. So both are convex. Okay. So okay, so we could stop there and say, okay, fine, both are convex, so what? Right. But it turns out that this one you have learned how to solve, this one explicitly you may not have learned how to solve, and that problem to some extent sometimes is more challenging, and I will tell you why. Well, for one, the intersection may be empty, right. I could have a situation like so these are the half planes and maybe another half plane like this, and clearly, oh sorry, this is not that clear. So and I have maybe another half plane like this. Now the intersection of these half planes is clearly empty, right, because this is the intersection of these two, and it's below basically, and this is completely above. So the intersection is empty actually. So it could be an empty structure. So the final output is empty, right? There is no structure. Not, I mean, empty set is also convex, that you can say, but then apart from that, second, those of you who have done a course in some operations research or linear programming, are you heard about linear programming? You have done it in school. Come on. Optimization of a linear function with respect to a linear constraints, right? So you can basically, that problem, intersection of half planes, that is the origin of the problem, that these are the constraints and I want to find out the optimum point. The optimum point, although described by a linear objective function can be also thought about as, let us say, I want to find the topmost vertex, in which case basically my linear function is, parallel to the x-axis. Okay. So that could be my objective function. And you can always transform the coordinates to say that my my linear function that I am trying to optimize is parallel to the x-axis, which means that I have to find the topmost point. So linear programming is very much related to this intersection of half spaces, that I need to find the topmost point of the feasible region. Okay. So and it is a very challenging problem and also a very useful problem. So in particular in high dimensions, but there is, by the duality we can, I can show you something which is quite interesting, that if I have an algorithm to solve the convex hull problem, okay, I can actually solve the intersection of half planes. I am not saying that I will solve the linear programming problem. Linear programming problem is, well, somewhat easier than intersection of half spaces, because here I have to compute the entire region. Okay, in linear programming I only have to report the point. So let us forget about the linear programming, that was a motivation. But if I look at this problem of intersection of half spaces and the convex hull problem, here is the connection. Okay. So given a set of points, I can apply the dual transform, okay, and define a set of lines. Okay. And then this structure that I have of the convex hull, let us look at the so you know about the upper and lower hull. So if I take the leftmost point and the rightmost point and draw a line through them like this, okay, then this portion is called the upper hull, this portion, and this is called the lower hull. Right? You must have seen this definition, no? But anyway, when you haven't, this is one way to think about, designing an algorithm for convex hull in 2 dimensions. Higher dimension is harder to define. So that I take the leftmost point and the rightmost point, which I can easily find out. And if you look at the line joining them, look at the part of the hull above this, that is called the upper hull. This is the lower hull, and they are symmetric. So you can, if you know how to construct the upper hull, you can apply the same algorithm to construct the lower hull. Okay, so you can focus only on constructing the, let us say, the upper hull. Now, so this upper hull structure, okay, is this chain, right? This is the upper hull structure. This is this chain. Okay. Now, if you look at the corner points of the convex hull, okay, when I apply the dual transform, see the corner point is what? The corner points are basically that you can draw a supporting line through that, right? Let me use a different color. So a corner point essentially is a line, is a point through which I can draw a line that will not intersect the convex hull. Okay. And the boundary of the convex hull is basically some supporting lines, moving like this. And so this supporting line is like tangent, right? So onto this corner point, if I move it a little bit, that's fine. But if I have an edge of the convex hull, that supporting line goes through 2 points, so it cannot be perturbed. So constructing a convex hull is basically like finding those supporting lines for consecutive points. Now, when I go to the dual plane, okay, so I have the notion of d of L, okay, and each point basically becomes a line, right. So there will be a, let us say this is p's of I, so this is d's of pi. So this line will become some kind of point when I go to the dual plane, and this point will become a line. Okay. Now let us try to interpret what this line is. Okay. Now this point pi, okay, so p of I is below L, right, and by our property of the orientation, above below property. Okay. D's of pi, D's of L implies D's of L is below D's of P's of I from the above below property of the dual transform. Okay. So, these points basically become, let us say, something like I am not drawing all of them. And finally, the, let us say if I am looking interested in these are the half planes, suppose. So, this is basically my intersection, right, the intersection region. So, this basically this portion, right. So, the points have become lines. Okay. Now, if you look at the intersection of this structure, sorry. So, this is the convex chain defining the intersections. Okay. Each intersection point, sorry, not each corner point of this is an intersection of two lines, right. The two lines are coming from the points, basically those are duals of points, right. So, one observation is, clear observation is, intersection points correspond to lines passing through, okay, so I need some notation. Intersection points, let us say, let us use P prime. Okay. So, P prime, now P prime is the intersection point of two lines, right. So, suppose this corresponds to two lines Li and Lj. This is Li and this is Lj. So, this intersection point then must correspond to a line passing through D's of Li and D's of Lj. That is, this is a line that passes through 2 points. Okay. So, if you look at the intersection point P prime, okay, that must correspond to essentially a line passing through the dual of those two lines because of the incidence property. So, what is emerging is that these corner points correspond to exactly these intersection points that define that chain. Okay. And you can actually use the above below relation to show, although these are half planes and not lines, but you can actually show that the upper chain here would correspond to that upper chain there. So, if I am able to construct the convex hull of the set of points, suppose I am given the problem to construct the intersection of half spaces. What can I do? Transform the lines defining the half spaces to points, construct the convex hull, and from that convex hull I can read out basically this structure. And what happens if it is empty? Okay. The emptiness can also be handled from the same thing. Emptiness basically falls out as you will find that the convex chains that we have will look like something like this. So, this will basically show. So, I am only showing the relationship between the upper hull, right, and the upper chain there. So, I showed the relationship between this and that. Now, if that portion is empty, okay, it will come out to be something like of this sort, that it will be empty, correspond the two chains will basically not intersect at all. But separately I can construct the two chains, and then I can easily find out whether they intersect or not. If they intersect, then it will be like this. Right. So, when should I stop? Okay, 5 minutes. Okay, fine. Okay. Good enough. Okay. So, I am just giving you basically how powerful this dual transform is to solve problems that map points to lines and lines to points. Right. So, let me close with, I think in 5 minutes should suffice. Oh, this one I said, look, I mean, I have a correspondence between this chain and this part, okay? But I said, what happens if the intersection is empty? If the intersection is empty, it will basically come down to this, that I will find these two chains from the convex hull which don't intersect at all. This has no intersection with this, right? This is the empty structure, whereas the one that is non-empty will give you a structure like that. You just have to, if you actually write the algorithm, it will come out like that.
It is only limited to line and point?
No, the dual transform applies to any dimensions. Okay.
For any curve can it be applied?
For any?
Like the dual of a line in a point,
Mm-hmm.
and dual of a point in a line.
Right.
Instead of line, you can make a curve. Can I apply the curve?
Curve, okay. Well, I mean, you have to basically then look at the dual transform as a union of points. See, dual transform is always defined. So, there is a dual transform of a curve also, but it's not going to be as nice a structure as this one. So, I can always think about a line as a set of points, right, and individually I can apply the dual transform.
And take the summation.
Yeah. So, for instance, disks etc. will have some dual transforms, which is a closed structure. Sometimes be closed triangles will have an open structure. So, it's the same thing, but you just intuitively it's not that easy.
It happens that if a convex structure can be transferred to convex.
That is what is happening here. That's the property I used. That is the property I used. Yeah, sure. Yeah, right. So, this is a point basically that is on the boundary of the intersection, right? And this point will correspond to some boundary point. Because this is below all these lines, and this is also sort of above or below all the lines. So, that's basically the analogy. I am saying a corner point here would correspond to a boundary point here using the above below relation, and therefore, I can read out this structure from this structure. See, this line is above all these points, and then this point is above all the half spaces. That's the way to read it out. What is the dual of this? The dual of this is this structure basically. So, this structure and this structure are exactly duals of each other. Okay, so let me go back to this transformation again. So, where is it? So, let me go back to the transformation and show you how the lifting transform can also be derived from here. So, when you did the Voronoi diagram, okay, so let me use the same page so that I don't have to draw again. So, I am doing the one dimensional analog of the Voronoi diagram. Okay. So, I am given a set of points. Okay. Now, in 2 dimensions, basically this is a plane and I project it onto the unit paraboloid, right. In the 1 dimension also. So, just to keep my diagram simple, so I am going to basically just draw these lifting transforms. I am lifting them to the paraboloid, okay. And then I draw these tangential lines, right. So, suppose this is A and this is point B. So, what do? You draw all these tangent, okay, and if you draw that intersection. So, I do not know, have you done this transformation actually? Right. So, this is the same transformation drawing except that it is in 2D. Now, what you can do using this dual transform, you can show that the distance between, so this is basically point B comma B square, right. So, the distance between A and B okay, and the distance between this point and this line, okay. So, this line let us call it L, okay, and the distance between vertical distance between this point, that is the projected point B comma B square and L. These are actually related by a square. You can just do the computation. Okay. So, I had it done. Maybe I can just do it. So, let me do it. Okay. So, distance between A and B is B minus A, right. Okay. Distance between this point and L, can you tell me? So, this line has a equation y equal to 2ax minus a square. So, if I use x equal to b, okay, so that is this point has a coordinate 2ab minus a square, right, from that line, okay, and then you just subtract it. So, it is b square minus 2ab minus a square, that is equal to a minus b whole square, right. And this is the key to the lifting transform, that this distance, okay, and this distance are related by a square. And therefore, basically what is happening is that from this point, if I want to find the closest point, then B is transformed, B is mapped to here, and you look at all the other tangents, and the one that is closest is the closest point, because the distances are square, exactly square. So, if the distance is larger, the square is also larger. So, it is proportional to that exactly, and that is precisely what the lifting transform basically exploits, and this relation holds for higher dimensions also. So, therefore, it exploits that. So, if you look at the transformation of the higher dimension, so again let me make sure that I follow the notations. Okay. So, I will just end with this. So, dual transform in d dimensions. Okay. So, d of A1, A2, A3, AD is XD equal to 2x1. This is the dual transform in the dimension D, right? And of course, the inverse is also defined like that. You halve everything and take the negative of that, right? So let me stop here.